In calculus, we're going to encounter a lot of different functions, and what I have here is like a gallery of some of the basic functions. Up here at top we have like a linear function, lines. This is like the basic form of a linear function. Of course, the slope and the y-intercept will change how it's shifted or how it's tilted. This is a quadratic function, or the basic one is just x squared, and of course this thing can move around. You can add coefficients to the x, you can add other terms. This is the basic cubic function, which is x cubed. You could have a fourth degree, which would look like the quadratic, but it would rise faster and be flatter on the bottom. A fifth degree would look like a cubic, and so any even power would look like the quadratic and have that sort of behavior where it's coming down and going back up. And then any odd power would have the form of the cubic here, where it kind of comes down, flattens out, and then turns around and keeps going like that. One thing is higher degree polynomials can have other terms with other powers, and these things go up and down, okay? And the number of turns they make will always be one less than the highest power, which is the degree of the polynomial. Okay, so their end behavior, so like a fifth degree polynomial, the end behavior will be like this cubic. It'll come down from this side and turn around and come back down. Okay, but a fifth degree, it will turn no more than 4 times. Okay, it doesn't have to turn 4 times, but it'll turn no more than 4 times. And so here, this is a square root function, and boy, this one's hard to see, I think, on there. It kind of goes up like this, and what it is it's really a quadratic on its side, but it's only this half right here, and you're not rotating it. What you're actually doing is you're taking this graph, and you're taking, here's the line y equals x, and this graph, you're just taking this side here, and you're reflecting this through the line y equals x. Boy, it's really hard to visualize that, but if I held these two corners and flipped it over like that, and it were see-through, then it would look like that, okay? This is the same thing done with the cubic equation, okay? Again, this one's hard to see. It goes down like this, and so it looks like a cubic equation on its side, but here you can see you're not just rotating it. You're not just turning it like this, because you wouldn't get this, would you? You're actually you're holding these two corners and you're flipping it like that. What you're really doing is you're switching the x and y axis around. So this becomes the positive x-axis, and then this becomes the positive y-axis. So these are inverses of these two here, okay? Inverse functions. They undo each other. So if I squared something and then I put it in the square root function, I'd get back to x. Or if I cubed something and then I put it into the cubed root function, again, I would get back to x. Okay, and this again is hard to see here, but this is known as the inverse function. And it's f of x is equal to 1 over x. And see, these are asymptotes, so basically as x gets closer and closer to 0, 1 over x goes off to infinity, or negative infinity. But as x gets larger and larger, it goes down to 0. Okay? And so these are asymptotes to the function. Okay? And it gets closer and closer to 0, infinitely close to 0, but it never touches it. Okay? And that's f of x is equal to 1 over x. And this is the exponential function. And this in particular, because this is what we're going to use in calculus, this is f of x is equal to e to the x. And e is like the natural base, and it's an irrational number. It's like 2 point, I don't remember, 2.8. Well, here, I got my calculator with me. So, e, it's like 2.718, 281, and it keeps going. This is an irrational number, kind of like pi, and it's called the natural base, and it plays a huge role in calculus and science and a lot of things. And oftentimes it's derived when you're using the compound interest formula, and you can compound your interest, let's say once a year. Quarterly would be 4 times a year. Monthly would be 12 times a year. Daily would be 365 times a year. Every second would be, a bigger number. Every nanosecond, and then every instant. And once you start calculating it every instant, once you start compounding it every instant, then that's continuous compounding, and you have the continuous compound interest formula, and it's that the amount in your account is the principal times e to the rate times time, and there's the natural base shows up there. Okay, and what we're going to find is this is going to be the only function where its derivative is equal to itself, and the idea of the derivative is the rate of change of the function. Okay, so it's equal to its own derivative, and that's a special role for the exponential function here. Okay, so you're just raising this number, in this case this number, to the x power, and so as x gets smaller and smaller, you get these negative exponents, right? Which is, if I have e to the negative third, that's the same as 1 over e to the third, right? And so as you go off to negative infinity, this thing's going to go to 0, so it gets infinitely close to the axis. But then as this gets larger, like e to the third, let's see, oops, we're already up to like 20, and this can get 20.0855. Okay, but as this gets larger and larger, it's just going to go off into infinity, and so it approaches this axis asymptotically, and this way it goes off into infinity. Okay, so now the natural logarithm is just the inverse of this. Okay, again, you're not just rotating the graph, you're taking these two corners and you're twisting it around, and you're getting this. So this thing here, you can't have any negative numbers in here, or even 0, right? But when you're close to 0, you're kind of going down to negative infinity. And I should say that this here is always 0, 1. Because when you raise anything to the 0 power, you get 1, right? So if you put in 0 for x, e to the 0 is 1. And this thing will always be 1, 0. And then, so as you get bigger than 1, you rise up, but it takes place very, very slowly. Okay, so between 0 and 1, you're going off to negative infinity. Greater than 1, you're rising up, but you're doing it very, very slowly. And that's the natural logarithm. Then the absolute value equation, if you look at this, this is a lot like this, okay? But when you take the absolute value of x, this is f of x is equal to x, so the negative x's over here are negative values. But here, when you take the absolute value of negative x, it's positive x again. So it's reflecting that over there. So it's bringing this up here, right? So that you have it's a V shape, and that's the absolute value function. Okay, so let me set that there, and what you might want to do here for a minute is pause the video and see if you can state the domain and the range of each of these functions, okay? And then start it up again, and then I'll explain them. So okay, so let's look here. The domain is negative infinity to infinity. The range is negative infinity to infinity. This one, you got this parabola, right? The domain is negative infinity to infinity. There's no problems there. But the range here is from 0 up to infinity, including 0. Okay? This one, the domain and the range is negative infinity to infinity. This one over here, the domain and range are 0 to infinity, including 0 on up to infinity. Okay? This one, the domain and range are negative infinity to infinity. And this one, the domain is all real numbers except for 0, because that's going to give you a 0 in the denominator. And the range is all real numbers except for 0, because this thing can never be 0. Okay, it can get infinitely close but never quite touch it. So the exponential functions here, the domain is all real numbers, but the range is 0 to infinity, not including 0, because it's never going to quite touch the axis. And then the natural logarithm, the domain is going to be 0 to infinity, not including the 0, because it approaches it asymptotically. But the range is negative infinity to infinity. Okay, so they're the opposites of each other there. And then the absolute value is the domain is all real numbers, negative infinity to infinity, but the range is 0 to infinity. So a lot like this. It's a lot like a parabola, except it's not curved, it's straight, it has that sharp edge where it makes a turn. Okay, so those are some basic functions, and I'll use some of these in the following examples here. So what we're going to look at here, and I'm going to go through this rather quickly because you've probably seen it before, but we're going to look at the shift in graphs. And I've kind of briefly talked about this in some earlier videos. But this is what you do when you want to move the graph around. This is how you can change the function. And I'm going to just show this with examples. Let's start with vertical. Vertical shifts. These are the most intuitive. So if I want to move a function up or down, okay, so I'll do x squared, and then I'll say plus 3. So basically, the idea, and I'm just going to sketch these out quickly. So this would be like y equals x squared. And that's like the basic function. So this plus 3, every value, every ordered pair here gets moved up 3 spots, right? So the new parabola is going to be like this. Okay. So let's say I have y is equal to, we'll say, the square root of x minus 2. Okay. Well, this is like the normal square root of x. Y equals square root of x. The minus 2 is going to shift it down. Each one of these ordered pairs is going to move down 2 spots. So I think of this as being the vertex, and I'm thinking of the vertex moving up here. I'm thinking of the new spot that it's going to move to. Well, this is kind of the reference point on this graph, and it's going to move down to. So it'll move down like that. So it's just shifting the whole graph down. Excuse me, down. Okay, and those are vertical shifts. It just moves the graph up and down. The point here is this is something added or subtracted to the outside of the function. Okay, here's the function. You're adding and subtracting it to the outside of the function. Okay, well, we also have horizontal shifts. Okay, so this would be something that is added or subtracted inside the function. Okay, this would be something like, we'll say x minus 2 quantity squared. Okay, the plus 3 is on the outside of the function. Here, the x minus 2 is on the inside of the function, inside this parentheses, right? And so this is basically going to be like this. This is the basic function, right? Y equals x squared. Now, you might think minus 2 would move it over this way 2 times, but it's not the way that you would think. That minus 2 actually moves it to the positive direction 2 times. So this would be like a parabola that comes down and touches 2. So this is moved over to this point like that. So it's a horizontal shift, but it's opposite of the sign here. The best way, that's kind of confusing, the best way to think about it is when you set your clock back, you gain an hour of sleep, right? When you set your clock forward, you lose an hour's sleep. So if you add 2, this is kind of setting your clock. This is doing the reverse behavior. But not so with this. This is going the direction that you think. Okay, but this is reverse, counterintuitive. Let me try y equals, let's just do e to the, we'll just say x plus 3. So now, see, this is being done, the plus 3 is being done inside the function, okay? Because the x is up here as the exponent, it's like you're doing the plus 3 inside the function. If it were being done on the outside of the function, it would be here. In fact, I'll add one like that. We'll say x. This is a horizontal shift. That is a vertical shift. Okay, so let's look at this. Okay, so normally this is like an asymptote here where it goes through and then it goes through this point and it goes up. And this point here, that's the point 0, 1. Any exponential function, no matter the base, will go through that. So what I can do is I can think of moving this point over, kind of like I moved the vertex over. So I'm going to, this is plus 3, so I'm going to move it back 3. Okay, 1, 2, 3. So this point is going to move over there, okay? But I also have the plus 1, which means I'm going to move the whole graph up. And so I'm going to also take this thing here and make that the horizontal asymptote. Okay, and so this is like 1, 2. So it'd go through like this. So then this whole graph would be like that. Okay, so in the case of this exponential graph, I move both the asymptote and this point, kind of those two together to kind of see. So I'm really this is I did that wrong. I actually did it wrong. Okay, here's what I should have done. I'm sorry. So I'm moving the asymptote up. And this one's maybe a little harder than these, but I'm moving the asymptote up, but I'm also moving this point over. So this should have gone right here. So this is not the right graph. Let me actually, I'm going to do it again on the back. Sorry about that. Good to know, even your teacher makes mistakes. So so this axis is going to be moved up. The x-axis is going to be moved up 1. The point that's normally here is going to be also moved up 1, but over 3. So it would be like right here. So it's almost like another way to think of this is you're moving this up 1, like this origin up 1 and over 3. So it's like that's the origin, and this is like the new axis, right? And then this thing is going up like that. So this one was like this, and this one would be like that. So shifted back and up. So that one maybe was a little more confusing there. But those are vertical shifts and horizontal shifts. Okay? So then what we can do here is we can we could also flip a graph over. So let me do negative x squared. Okay, so when you put a negative on the outside of the function here, so this is like the normal y equals x squared. The negative on the outside is going to flip this over. Y equals negative x squared. Okay, so that's kind of a flip through the x-axis. So then you could do a bunch of these together. You could do something like negative x minus 5 squared plus 3. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 8, 9, 10. So nice big graph. So this is a whole bunch of transformations. So I'm going to just kind of, this would be like the y equals x. Okay. And then I could shift this over. That's inside the parentheses. I'm going to shift it to the positive side. 1, 2, 3, 4, 5. So it's like right here. Right? And this would be like y equals x minus 5 squared. And then I can flip that upside down. That's the next thing being done. So this would be y equals the opposite of x minus 5 quantity squared. Okay, but then this whole graph is shifted up 3, right? So 1, 2, 3, like this. And that's my final graph. Y equals negative x minus 3, or x minus 5 squared plus 3. So that's a whole bunch of shifts done to it. It's shifted over, flipped, moved up. Okay. So all of these that I've done here, these are known as rigid transformations. They're the easiest because they don't affect the graph at all. So usually we can just use this here. When I did this, I just kind of drew my graph, so I don't really know how accurate. I didn't plot points, so I don't know if this should be going down further, you know, quicker, or if I should have it more spread out. Okay, I'm just making the point that I'm taking the regular parabola and moving it there. I'm not worried about the scale on here so much. Okay. And the reason is because this is a rigid transformation. It doesn't change the shape of the graph. So like this is 5, 3. What's really the most interesting is the vertex is now this point. The graph is flipped over, and then you're moving it up. Okay? Up 3. So those are rigid transformations. Let me finish up here, and then I think I'll give you enough to do the homework, and then you'll see more and more of this sort of thing as we go through the class. But what I want to finish up here with are, these are kind of non-rigid transformations. So these are stretches and compressions. Okay, so let's just say that A, we're going to let A be greater than a positive 1. Okay. And so so A is greater than a positive 1, and or you know what? I'm not. Well, let me do that, because I'm going to state here. So let's say A is greater than a positive 1. Then if I take and I multiply f of x by A, that's going to stretch it. Okay? And if I multiply it by 1 over A, that's going to compress it. Okay? And similarly, if I take and I multiply the x by A, okay, if I multiply the x by A, so it's inside the function, this is going to compress it. And then if I multiply x by 1 over A, like this is going to stretch it. Okay, so in a sense you would think multiplying this by a bigger number is going to stretch that out. So let me show you. Y is equal, we'll just say 3x squared, right? If this is like your regular y equals x squared, that's your regular one, then this thing's going to rise up 3 times as fast. So this would be y equals 3x squared. Okay, so in other words, it's taking that graph, stretching it up. So any one of these y values is 3 times as big as the normal one. Okay, so it's stretching it up. But if I take 1 over A, so if I do this, y is equal to 1/3 x squared, right? Then this would be like the regular one. X squared. But now this thing is going to be, compressed, right? It's squashed down. And the reason, of course, let me move it up here. The reason this is squashed down is each one of these is 1/3 of what it was before, right? And so that squashes it, or it compresses it down, okay? Now this is the opposite, okay? And I'll use x squared again. So if I do y is equal to 3, we'll put 3x inside, okay? You know what? This should be stretched vertically. And this is compress. Both of these are horizontally. Okay, both of these are, so this is going to compress it horizontally. Like this would actually be like 9x squared, right? So in other words, if this were the regular, okay, y equals x squared, well, this would really be stretched up, right? In this case, y equals 3x squared, okay? But that stretching it up is compressing that horizontally, isn't it? Not stretching it horizontally. And then if I have, you know, let's do like y equals 1/3 x squared. So this would actually be like 1/9 x squared, right? So this is like your regular y equals x squared, and 1/9 would be like way out like this, but it's 1/3 x quantity squared. And so what is it doing? It's stretching it out horizontally. Okay, it'd be compressing it vertically, it's stretching it out horizontally. So that's the way that this plays out with the x squared. These could play out in other ways, because you might put in something inside here, but it might not be able to come on the outside. Like I might not be able to put it on the outside there, but it's still going to compress and stretch opposite of what the vertical compressing and stretching does. So these are non-rigid transformations. In these cases, you really almost have to plot points if you want to get a picture, an accurate picture of the graph, and know that it's different than normal. Otherwise, if you're not actually plotting points, you would probably want to show the other one before you show the one that you're stretching or compressing, so that you can compare the two. Okay? Because you can actually change windows. Like this could just be this here could just be the tip of the normal parabola, and it would look like this, right? So by changing windows or changing scales, you can also make these differences as well. Okay, that's why you have to be careful as you're using technology, that your graph could be affected by the window size, the way that it looks. So like a circle, if the two scales are not the same, your circle might look like an oval, for example, or your semicircle might be all stretched out. Okay, so the rigid transformations are the vertical, horizontal shifts, the flip, and those are, I think, pretty easy. And these are okay too, but they do involve a change in the shape of the graph. So the rigid transformation is taking the basic graph, moving it around. These are actually distorting, changing the shape of the graph.